I'm going to talk about ways that we use data to support water resources decision making, and I'm going to go through several examples of projects that we've conducted in the USGS Virginia and West Virginia Water Science Center that make use of these types of data. To talk a little bit about just data in general, this is some of the types of data that we collect in Virginia and West Virginia. So the top left, you see the stream gauge network that we manage across the two states. Most of this data is real-time data. All of this data that I'm going to talk about is available through the USGS website. Bottom left is groundwater monitoring data, and bottom right is water quality data that we collect. Data in general for managing water resources and making decision-making for water resources, long-term data is critical. We have a lot of variability in the system, variability in precipitation and runoff from year to year, variability from season to season. So if you're trying to understand a system with all of this variability going on, long-term data is critical. The other thing you need is spatial data. There's also a lot of variability in terms of land use and geology and other features. So the more data points that you have over space, again, to try to understand the system better, to take out some of this variability, the better off you are. In general, the program that we have in Virginia and West Virginia can kind of fall under these four categories. Understanding ecosystems and predicting ecosystem change. A lot of this has to do with water quality. Understanding climate variability and change, water availability and water use, and national hazards, risk, and resilience assessments. One thing I'm going to tell you about the program that the USGS Water Science Centers have, a lot of the work that we do is in cooperation with state and local agencies, where they're providing funding to us. We match that funding through what we call the Cooperative Matching Fund, and we do work on a very specific question that they need help in answering. So a lot of the work that we do is really applied research. The first problem that I'm going to talk about is some work that we're doing in the Hampton Roads region. Hampton Roads is faced with a severe sea level rise issue. You can see from these numbers where sea level rise in the Hampton Roads Chesapeake Bay region is significantly higher than it is in other places on the East Coast, and in some cases is twice as high as what we see in other places on the East Coast. There are a lot of things being impacted by this sea level rise in the Hampton area. There's 1.7 million people, significant military infrastructure, historic resources. What you see on the bottom left is Jamestown Island, and then also coastal marsh ecosystems, which both help buffer storm tides, but also are a critical resource for the Chesapeake Bay. All of these are threatened by sea level rise. And here's another slide that shows just the magnitude of that sea level rise. More than double what you would see globally is occurring at Sewell's Point, which is in the southern end of the Chesapeake Bay. And why do we see those levels of sea level rise? A big component of that is land subsidence. So we not only have higher levels of the ocean, we have the land sinking as well. And the land is sinking for two reasons. One of the reasons is called glacial isostasy, glacial rebound. When the glaciers were on the land 10,000 years or so ago, they pressed down on the land and created a bulge out in front of them, much like you would put your hand on a balloon and create a bulge in the balloon. As the glaciers receded, the bulge is actually still going down. So that accounts for part of the land subsidence that we see in the region. The other part of the land subsidence is due to groundwater withdrawal, and this slide shows some of that subsidence. So the places where the subsidence is the largest, down near Franklin and in West Point, those are areas where large amounts of groundwater are being withdrawn. And the removal of the groundwater is causing the subsidence of the aquifer system, particularly the clay layers in the aquifer system are getting smaller, are shrinking due to groundwater withdrawal. So we want to understand this better overall for a number of reasons. Many localities in this region are taking action to try to protect themselves against sea level rise. But we see that sea level rise is not going to be just one number across the region. It's going to vary. It's going to vary with land subsidence. So some localities are actually going to have to deal with higher levels of sea level rise than others. So we really need to understand this, the subsidence better. It also might be possible to impact the amount of groundwater that we're withdrawing in different locations to try to reduce the amount of subsidence that's occurring in different areas. So you can see this data actually only goes up through 1970, so we don't have a lot of data since then to better understand what's occurred since the 70s. Some of the actions that we're doing right now in the region, we've added 25 new tide gauges over the last couple of years. A lot of the funding for those tide gauges were provided by Hurricane Sandy funding for the actual installation of tide gauges. A number of localities, 10 localities, are helping to support the funding of this, the operation of those tide gauges. At each of those tide gauges, we're also using GPS to identify what the land surface is doing. So we're not only getting how the level of the tide is changing over time, but we're also getting the change at the land surface over time as well. Emergency managers, local emergency managers, use this data to give them a better understanding during a storm event as to what areas might be flooding and what roads might need closure, etc. We're also installing what we call extensometers. We have refitted 2 existing extensometers in the region and are installing a new extensometer beginning next month, actually. An extensometer is basically a well that goes all the way down to the bedrock in the region with a steel rod inside of the well. So as the aquifer system around in that area subsides or shrinks, gets smaller, the steel rod actually sticks out of the ground more, and we can measure the amount that the steel rod is sticking out of the ground and get a better understanding of what the subsidence that's occurring within that region. And move on to a different topic. There's a significant effort by a number of partners, state and federal agencies, to try to improve the water quality in the Chesapeake Bay, to try to restore the Chesapeake Bay. One of the key pieces of information that's used in that effort are what are the trends in nutrient and sediment loading to the bay. And this slide basically shows nitrogen loading to the bay over time to give us an idea of where things are improving, not improving, or potentially degrading. This ends up being a critical tool overall. State agencies are spending a considerable sum in terms of best management implementation, practices to try to improve water quality, the quality of water improving the bay or reaching the bay. So this data helps us understand where those efforts might be succeeding, where maybe they are falling short, to help us change the practices as we're implementing them over time, and ends up being a kind of a critical information product for the effort as a whole. And this is just another way of showing that same data. The network that we have in the Chesapeake Bay has over 81 stations right now, and it's kind of a unique network. This data is just for 2005 to 2014, but a lot of this data goes back to 1985. So we can see the trends and the improvements that have been occurring since that time. If we look at smaller scale, we also have a pretty extensive network in Fairfax County. Fairfax County is trying to restore the water quality in a lot of their local streams, and the water quality is impacted by urbanization, so you're getting down cutting and just a degraded water quality in general. So they are implementing a number of practices to try to improve that water quality, and we're helping them monitor what the effect of those practices is over time, and by providing them information about the trends, what's working, what's not, hopefully improve their overall program in terms of as they try to expend significant resources to improve the quality of water in these streams. And here you can see the extent of that network. This is a very nice network that we have in the county, and again, we feel like it's going to help them improve their management as they try to restore the water quality in the streams. Moving on to kind of a different topic, the Great Dismal Swamp down in southeastern Virginia, kind of down in that Hampton Roads region again. If you look at the top right, you can see lines kind of crisscrossing the swamp. Those lines are canals that were put into the swamp. The result of those canals is that water levels are dropping. Basically, the swamp is starting to dry out, and the drying is having a number of effects. One, the vegetation types are changing in the swamp to vegetation that's more or less tolerant of, more tolerant of drier conditions, or they don't need the wet conditions. The other problem is fire. As the peat in the swamp dries out, it becomes a fire hazard, and if that peat catches on fire, it can burn for months at a time. So the refuge is trying to understand how to better manage water levels within the swamp. And they have these water control structures that they operate, and other places where they're considering installing water control structures. And again, they're trying to improve the overall habitat by making the swamp wetter so that the original vegetation can again thrive. They're trying to reduce the risk of catastrophic fires, and you can see some of the result of the fires in the bottom right. They're also trying to determine whether they can help reduce downstream flooding. When they do get major events, there is some downstream flooding downstream of the swamp, and they're wondering if whether they can manage the water control structures in a way to reduce the amount of flooding. So we're basically helping them understand the overall hydrology of the system, collecting groundwater and ditch water levels, precipitation and soil water moisture levels, to help them better understand what the impact of changing the water levels with the different water control structures are, or if they were to implement other water control structures and install them, how would they potentially improve their ability to manage the water resources within the swamp. We're also developing basically a hydrologic model that will allow them to simulate different levels at the different water control structures to get a better understanding of the overall impact in the swamp. An offshoot of some of the data that we've collected within the swamp is that there is another group within USGS and within the climate program looking at ecosystem service assessment and carbon monitoring within the swamp. And basically they're looking at carbon sequestration in the swamp. Because of the drying, a lot of the peat is starting to degrade. So they're assessing what levels of carbon might be being released and what levels of carbon could be sequestered if the wet conditions were restored. The last project I'll talk about is one where we're looking at characterizing the response of stream flows to precipitation and climate. And really this is a drought response project that we conducted in Virginia. Looking at seeing if we could extend the lead time for drought response. Can we essentially predict drought 5 to 6 months in advance? One thing we learned from a project that we were conducting in the Shenandoah Valley in several counties who were interested in how much water they had. They were facing a lot of population pressure due to development, and they were interested in their water resources. How much water did they have? How much construction build out could they sustain? But in studying those counties, we started to understand that there was a direct connection between rainfall during the winter, during the recharge months, and how much water existed in groundwater wells and in the streams. And basically in this area, all of the recharge to the system is rain that occurs during the winter. After leaves come out on the trees, there's very little recharge. Almost all of the precipitation gets captured by the vegetation. So this winter recharge period ends up being critical. And then we started to think, well, given that, could we predict what the summer flows would be in streams based on what the winter flows in streams are? Could we give somebody a probability that says if the flow in your stream is this much during at the end of February, what's the likelihood that you're going to have a drought problem during the summer? Basically trying to give people a 5 or 6 month lead time on drought, which is significant for a locality or for an industry that's trying to plan for a shortage of water that might occur during the summer when flows tend to be the lowest. That kind of predictability or that kind of lead time would allow them to secure water from another source potentially. And basically we were able to do that. We were able to basically establish that we can assess a probability, much like a weather prediction. We can assess what the probability of being below a certain flow is based on February, the flow in the streams in February. So again, we can give this region probably a 5 or 6 month head start on possibly being low in water. We've also looked at this method nationwide, and over most of the nation, the methodology that we developed here actually is applicable to the rest of the country. Thanks, Cassandra, and I guess we can move on to the question and answer part of the session.